Okay, so I think we can continue with this second talk of the morning session by Colin Guillarmou. He will tell us about how to construct Wess-Zumino-Witten models from probability. Thank you.
Okay, thank you very much for the invitation. Right, well, I will. So, Antti gave a mini course about, I think maybe Liouville, and in the last part of the course, he explained equation of Wess-Zumino-Witten H3. I heard it was a bit tough, so I tried to make it more friendly. Anyway, so maybe I should start with the nonlinear sigma model. Right, so what is nonlinear sigma model? So you have, let's say, in our case of dimension 2, you have a Riemann surface. So this is a Riemannian metric on the surface. And then you map to another manifold. I'll draw the sphere. So this is 2 dimensions here. This one may be higher dimension, so dimension n. And I will call m the target manifold. So we're going to look at the field phi, which map from a surface to a manifold, could be dimension. And then I put a Riemannian metric here. And you can look at the following path integral. Which is that if you look at functional over set of map from sigma to m, goes from map from sigma to m with value, let's say, in real number, and positive if you want to define probability measure. The nonlinear sigma model will be the path integral, at least should be an integral over the space of sorry. So, space of map from sigma to m. And then you put a Gaussian action, which is just a differential to the square. And here, this is at point x. You integrate with respect to the volume measure of the surface. So it's square root of the determinant of Gij in local coordinate. And here you're measuring this as a map from Tx m tensor Tx star. With respect, so this is the length with respect to this is the norm if you want, with respect to metric m. So you have the differential is a linear map from tangent space of sigma to the tangent space of m. So you can view it as an element in this tensor product. There is a canonical metric on this for each x on this vector space induced by just this little m and little g. So just compute it. So this is the action. And then you integrate over all possible. So this is the nonlinear sigma model. So in general, this looks like Gaussian, but this is really nonlinear in some sense. I will come to this. And this, in general, we don't know how to define probabilistically, except when the target space is, let's say, vector space, like Rn, for instance, or maybe a torus. If you take Rn and you model by abelian group, there is a way to do it using the complexified Gaussian free field, or maybe several complexified Gaussian free field. But if you map really to a space which has complicated metric here, or like the sphere, for example, In general, we don't know how to do that.
Is there an expectation this is always possible for any compact Riemann manifold M, or is it unclear?
Yeah, it's unclear. I don't know. I mean, at least there is no construction. So I think the physicists, of course, you can discretize the model, and physicists work with this, and they show it's a case, let's say, that there should be limit, but that's a problem. So now,
I heard people say that this is maybe not easy to complete, or so it doesn't unclear if it. I don't know what the expectation is.
mathematically, to us it's unclear. And now, the Wess-Zumino-Witten model is really a perturbation of this case. There's a special case. Oh, I should also say that the critical point of the action are just the harmonic map. So this is studied a lot in geometry. Critical point or what's called harmonic maps. So you're looking at fluctuation around harmonic map here with this path integral. So there is a special case which is when M is just a Lie group, G, a Lie group. In this case, there is a natural metric, M, which is a killing form. So for instance, example, take SU2. This would be the two cases I would be interested in, SU2 or SL2C, but of course we can take SLM or any more complicated group. In this case, if you want M of AB, if you take two matrices, it's just 4 trace of in this case.
It's free, yeah?
So here, if you take SU2, this is going to give you a Riemannian metric. And this comes from the compactness of the group. If you take SL2C, SL2C is the complexification of SU2. The M is not going to be positive definite, it's going to look like the Lorentzian matrix. So probabilistically, this guy looks much better, because then otherwise this would not be positive definite if you look in SL2C. But on the other hand, okay, the fact that the group is compact is tricky to make sense probabilistically. So now what Witten proposed, so okay, physics, this has been this model, and they actually, so I should say this case where you take a Lie group is called the Wess-Zumino model. Not Wess-Zumino-Witten, but Wess-Zumino. And this case is not a CFT. So what Witten and also Novikov, as I understood, Witten proposed a modification of the action so that you reach application to the action, to the Gaussian action, the nonlinear sigma model, to the Wess-Zumino model, which means that when M is, let's say, SU2, or SU2C, or more generally Lie group, so that it becomes a conformal field theory.
You mean the action is conformally invariant? The theory is.
The conformal theory, the field, quantum field theory is conformally invariant.
So the action itself is.
The action has a nice conformal property of not really conformal invariant, but has some sort of covariance. It becomes a CFT. And moreover, it's an interesting CFT because also it generates a new type of algebra, Lie algebra, of a new group of symmetry, which is called the Wess-Zumino. So you know that in any CFT you have this Virasoro algebra. It comes from deforming the complex structure of the surface. But in the Wess-Zumino-Witten model, there is an extra symmetry which somehow comes from the fact that you have a Lie group here. So what is this action? What is the Wess-Zumino action? It looks a bit strange from the beginning. So yeah, I should say.
So the sigma mode is not a CFT in the sense that it's massive, or what? Or it depends whether...
It's okay. In physics, they say that they do not satisfy the conformal property.
But, okay, the structure then depends on the choice of the Lie group, or I mean, the properties of this quantum field theory is not a CFT, then it depends on the details of the...
Yeah, it depends of course on the Lie group, but just it does not satisfy the usual axiom that, if you look on the sphere, you have Moebius invariant, something like this. But there is a cool philosophy using a normalization group to start from the non-linear sigma model, and somehow you should maybe converge, I don't know, or depends maybe on the group if it's compact or not, to the Wess-Zumino-Witten model, which is like this perturbation. So now, actually, let me write the Wess-Zumino action. So I said this is this d phi square with this trace here for scalar product. It's quite concrete. In this case, it's equal to 1 over 4 pi I integral on sigma of the trace. So this comes from this m thing time h minus 1 dZh wedge h minus 1 dc bar h. So here I view this as a one form on the surface with value. This is valued in little SL2. This is valued in the Lie algebra of SL2. So this means trace zero matrices. But this is a one form on the surface. So one form on the surface with value in the matrix. And then you take a wedge with this, you take the trace, you get a two form on the surface that you can integrate. So this thing is nothing more than this when you apply to this M here, to this thing. Because here, of course, I didn't say, but maybe it needs to be the Lie algebra in the tangent space, SL, or Lie algebra of the group. Okay, so this is the Wess-Zumino-Witten in this case. And now, what is the Wess-Zumino-Witten model? The one that Witten proposed. So I will add a W for Witten. Then you add another term to the action, and this term is as follows. It's given by 1 over 12 pi I times integral over x of the trace of h tilde minus 1 dh wedge h tilde minus 1 dh. If you're not very familiar with this matrix value form and so on, don't worry, I will be more concrete soon. This will be very explicit. So he proposed this. So what is x? So you start with your surface.
Sorry, can you repeat what H is?
H is just sorry. Sorry for that. I will write now H for the field phi.
Okay.
It's an element with matrix valued in the group Lie group H. In the Lie group G.
So it's okay. It's an element of SU2 parameterized by
so H.
The
H is just a map from sigma to G, which is either SU2 or SL2C. In the case that we interested.
And the first part is just this d phi squared.
Exactly. So this part
is a way of writing.
It's just a way of writing using this thing. Because you have this complex structure, Z and Z bar, so you can decompose the differential into complex derivative and anti-complex derivative. And this is basically what it is. So what is now this term? So you start with your surface sigma, and you view it as the boundary of three. This is a three-dimensional manifold compact with boundary equal sigma. So you extend it in a way. For instance, if you have the sphere, you can extend in a void. And you just extend h tilde is any extension to x. H tilde map x to G and H tilde on the boundary of x, which is sigma is nothing more than H. And fix any extension of your field. So again, this could be the sphere here, and the interior would be the ball. You extend, and you compute this thing. So here it's one form with value in the algebra of G. You take the wedge, so it's like your anti-commutative product. You take the trace, you get a 3 form. You can integrate on X, and you have it. It looks a bit strange because you have to extend. And okay, there is no unique way to extend. But what Witten explained is that this term, this action, okay, maybe I want to put a K here as well. So K will be the level of the theory. You can add a parameter here. The level of the Wess-Zumino-Witten model here. And what you can show is that in this case, at least in the SU2 or SL2, if K, it's a fact that you can check, if K belongs to Z, to 2 pi I Z, the exponential of S Wess-Zumino-Witten sorry. Okay, let me do it. I put a K in front of this. H. This one is actually independent of the extension. Independent of X and H tilde. So you have this term which looks non-local, it's a bit strange, but actually, as long as K satisfies this Z condition, you can check that this full action, and you multiply by K, is really univalued. That's not dependent on the extension. That's what
You still have the first term, which you cannot take the K out.
No, I take exponential K times the whole thing. So now I
divide the first term by
K is the level. K is called the level of the theory. So this will change the central charge, this K.
So K is in front of everything.
Yeah, sorry, this is in front of everything.
But the K is only in front of the second term, right? The first term does not have this.
No. The path integral, I want to put K in front of everything. To be a CFT. No, it's important that, it's important that this is the same K which multiply everything, so that, okay, I mean, if I take K equal 1, this is this is univalued also, but I can multiply, maybe K, sorry, not 1, but 2 pi I maybe.
So I will ask this question. Why do you divide by 2 pi I and then multiply by 2 pi I?
That's divided by 12.
But it's 2 and then 6. But you multiply by 2 pi I.
Normalization, you know.
And also why 12? I mean,
No, this is important.
I guess so. But
This is related to the structure of the group. If you take another group, you have to choose another.
so which group is this?
This is for SU2 or SL2C. Otherwise, it's related more or less to the volume of SU2, of the compact group, this constant. This is very important to choose the right.
But actually, the real value of the whole compact value is the action.
The action a priori is complex. And then, of course,
The first part is positive at least.
the first term is real because it's a metric. It's phi squared, but the other one maybe could be complex. In our case, you will see it will be real. But okay, so this is.
So I guess the point of writing this way is because there is no way of writing this as an integral over sigma.
In general, not, but in the case I will consider, it will be.
So you can write it as a boundary integral.
Because we will. Okay, if you do SU2 in general, you cannot. But we will consider this H3, which is a little changed to this.
The obstruction to write it as a surface integral is precisely because of this K, right?
Sorry?
The obstruction to write this as about surface integral is precisely because of this K.
So K has to be quantized for the group. In our model, actually K can be real because we will take a modification of this thing.
Okay.
So the problem, okay, probabilistically it looks much better to look at this SU2 because it's compact. Not probabilistically. To study the model, it looks much better to do this. Probabilistically, it looks a priori good because it's positive definite. It's, in some sense, it looks like Gaussian, but we don't know how to define. if we do SL2C, this is non-compact, then it's not positive definite, the action. So then for probability it looks very bad. So we cannot deal with this case. So what we do, this is something which was proposed by Gavetsky and Kupiainen a long time ago. And actually for many reasons, it's actually natural to look at a model. Now, at the moment we cannot construct these two models. Or G equals SU2 or SL2C. So we consider another case, which also is to be a CFT, is when you consider the manifold M to be the hyperbolic 3 space equipped with natural hyperbolic metric. And what is this H3? You can represent it as a quotient of two Lie group. It's the quotient of SL2C mod SU2. So this is this complexified SL2C is a complexification of SU2 viewed as a real manifold, as a real Lie group. And H3 is just the quotient of this. This is the isometric group of H3. So what you do, you look at what are these concepts. You consider SL2C matrices modulo SU2, and in fact this is nothing more than the SL2 matrices with, which are positive definite. Let me write what they are. So here what we're doing, we're looking, if you want, at the killing form on SL2C, it's Lorentzian, but we kill this term so that it becomes positive definite. The quotient, this is a Riemannian manifold. So
the symbol H3 stands for what?
Hyperbolic 3 space. So H3 is just, you can represent it as, this is something I will use actually. I want to represent it like this. Okay, this is the Upper half space if you want. That's C, gamma is the parameter in C. And then you have R plus. R plus, I want to represent it as exponential of the field, exponential of something. And then the metric, G hyperbolic is just phi squared plus exponential minus 2 phi times gamma square. That's the hyperbolic metric. So now, if you look at the nonlinear sigma model with value in H3, the nonlinear sigma model in H3, the action S, well, okay. The action, if you want, S of gamma maybe. This is going to be the integral of, well, actually dphi square with respect to G. So this is the square norm of dphi. This. That's exponential minus 2 phi. If I don't get it wrong, time d gamma square. Then I integrate on the surface. So this will be the nonlinear sigma model in H3. So you see that it looks very much like a Gaussian free field here, if you want to define the model, d phi square. And here it looks like a Gaussian free field in the gamma, but weighted by the other Gaussian free field. So it sort of smells pretty good if you know the Gaussian multiplicative chaos theory, because you have this exponential phi, and maybe there is something going on here. But this is not exactly clear how to define the path integral associated to this action. But this is what we try to do. So this is the nonlinear sigma model. So now this nonlinear sigma model is actually related to this Wess-Zumino action.
And also the second norm is the G norm.
It means that at each point x you...
Yeah, okay. There is the G min.
Okay.
How did Gavetsky and Kupiainen end up with this model, and specifically with this? I mean, this is very special of just H3, or is it more general?
Yeah, no, it's because you take the SL2C, you want to define the Wess-Zumino-Witten model, the action is not positive definite, because it's Lorentzian. So you kill by you model by the maximally group, compactly group, and then it becomes this hyperbolic.
So that was an attempt to make the model in SL2C
to be
more
positive
validated,
definite. Yeah, in some sense, okay. Probabilistically, it's nice because it's non-compact. So the field map essentially in this. You can think of this as two probabilistic fields here, E and gamma. It looks like two Gaussian fields. But it's still positive definite direction. It looks like Gaussian because you have removed this part which is negative actually.
But the CFTs you construct are related to the minimal models or no? These are other kind of CFTs.
Yeah, the central charge is going to be bigger than 1.
Bigger than 1, in all these cases that you mentioned.
Yes. So it's a non-compact model actually. It should have continuous spectrum, but it's non-unitary.
Right.
And okay, the reason why Gavetzky and Kupiainen looked at this is it's because it's a way to study. This was also proposed by Witten. It's a way to study the SU2 to first take this group for a reason I don't explain now. But
Witten proposed to do
yeah,
this.
because it's related to conformal blocks and blah blah blah. So he said there is a way, or Gavetzky, Witten, and Kupiainen, they have some heuristic saying that if you understand this well, you should be able to construct a scalar product on conformal block of this guy, and then maybe you can construct a theory out of this. And it's also interesting for other reasons. It's related to this analytic Langland program of Frenkel and so on. But anyway, let me come to maybe the construction, because maybe that's what probabilistic are interested in. So now, if I take this Wess-Zumino-Witten model here, and I try to, so again, H3 is this Gaussian. So what are the coset SL2C over SU2? So any, if you want an element in SL2C mod SU2 can be represented as H equal Q star. So it's a product of two matrices where Q is of this form, exponential phi over 2 exponential minus phi over 2 times gamma. So gamma is a complex number, phi is a real number. Yeah, I should say here, F is real. And here it's a 0, and here it's exponential minus phi over 2. So any, you can represent the coset as positive definite matrices with determinant 1, represented like this. It's so you get this parameter phi and gamma, and this is the identification with H3. This is how you represent H3. And now if you compute the Wess-Zumino-Witten action, this cool thing with this H equal Q star, you can check that, of course, if you multiply Q by, I don't know, by an SU2 matrix on the right, because of this Q star, it just disappears. So this is well defined somehow. You compute now what is the value of this Wess-Zumino-Witten model with this special H. It's a direct computation. I give you the formula now. And you will see that it looks very much like this. It's just a perturbation of this model.
So if you just do the Wess-Zumino, you get that thing exactly on the nose.
Yes.
You're going to tell us what is the next term that gets added.
Exactly.
Okay.
So you compute what it is. And it's kind of magical, it's related to your question, that actually we don't need this extension then. This would be very explicit in terms of phi and gamma. And this is related to the fact that H3 is contractible. So there is an argument that in fact, in our model now, if H is Q star, as above, you compute. And what you find is the following. So it's minus 1 over 4 pi integral of d phi square. So this is really, again, like the GFF. Plus 4 exponential minus 2 pi of x times d bar, if you want to take this d bar gamma. measure with G, and then you integrate on the surface with respect to the. So this is the action. So it looks very much the same as before, except that instead of the derivative of gamma, you just get the dz bar. Okay?
So what you wrote is the term that you add, or is the term that is the whole thing?
Sorry. Well, this is just as before, except that you have this dz bar instead of just.
Yeah, but this includes the effect of the orange piece.
Yeah. This is everything here. This whole thing is equal to this. Okay, so now we want to define probabilistically the path integral is equal to this action essentially. So now, okay, the idea is
So this action is not the same as the linear sigma of H3.
No. The nonlinear sigma is just this one. So here again, this is dz phi plus dz bar phi if you want. Okay, this should be a one form, so you should really consider it that dz bar plus dz phi dv, and then you take the square. There are two terms here in the derivative. There is holomorphic and antiromorphic, and in the Wess-Zumino-Witten model, there is only the holomorphic.
And this nonlinear sigma itself has not been constructed yet, right?
Okay, I think probably we should follow from what we do. But, we didn't really look the nonlinear sigma model. We really look the Wess-Zumino-Witten.
That one is not a CFT. So
No, this is not a CFT.
It's not a CFT.
Yeah. Okay, so now let me come to how we construct probabilistically this action.
At which step did the symmetry between Z and Z bar get broken? Like,
You have to call it like explicit computation. You see that?
this orange term breaks the Z and Z bar symmetry. Okay.
And the fact that H3 is contractible is important to reduce this term to something completely local and explicit. Okay, so how to construct this thing now? So I sort of told you, well, actually, you should think of phi as a GFF, and maybe you should think of gamma as another field coupled to GFF somehow. And the covariance of this field should be related to this phi. So what we will do, we will construct the marginals. We will first construct the law of gamma depending on phi. So I will do a bit of heuristic, and then I will give you the proper, the concrete definition. So in this story, there is, in this kind of problem where you have a sigma model, there is something a bit strange that you have to choose coordinate. The field is with value in not in vector space, so you have to choose coordinate. For us, the coordinate are this phi and gamma. And the construction looks a bit dependent on which coordinate you take. This is something which is really quite tricky, actually. And checking if you change coordinate, if you get the same object, is not clear at all in general. So what we will do is we will use this particular coordinate phi and gamma for the H, for this matrix H. So now, okay. So first step is to construct the path integral conditional on phi. So phi later will be a usual GFF. The following path integral. So I want to construct f of gamma exponential minus. I want to put a k here also in front of the action. K times s, so k over 4 pi. Integral of, well, the d phi square, I remove it now. And I look at this term, so it's 4 times exponential minus 2 pi of x times dz bar of gamma square of z and z square, and then I integrate on the surface dg. So I want to define this thing. So this looks like a sort of Laplacian. So what is the covariance? So this guy is what I will call Laplacian phi of gamma, scalar product with gamma. And what is Laplacian phi? It's actually a Witten Laplacian. So it looks like the covariance of gamma is the green function of a Witten Laplacian, except that the Witten weight, this phi, this phase, is the Gaussian free field. So now what is delta phi? Delta phi is just sorry. Yeah, okay. It's dz bar exponential minus 2p dz bar star. So this is the covariance operator. So now if you look at this guy, so how can we define this a priori? Let's assume that phi is smooth to start with. So this thing, the path integral with the gamma, well, we would like to define it like this. So f of gamma 0. So this should be the zero mod of gamma. So the element in the kernel, a priori the kernel of d phi is not 0. And if you look on the sphere, there is the constant. Plus something I will write gamma g maybe, depends on the metric. Expectation, so there will be an integral over c, expectation of this, d gamma 0. So in this case, the kernel is just actually c. And here it's the expectation of this gamma field, which is defined using the covariance of this. So I would like that the gamma of z and gamma bar of z prime equal the inverse of this operator. Z prime. And then, because it's a complex Gaussian, I also want that gamma z prime is 0. So these two conditions determine gamma. Let's say phi smooth. Okay. So okay, we would do like this, but remember there is the partition function to be considered. Like the determinant of this operator should appear in the Gaussian integral. So in fact here, to have a proper definition, I should add the determinant of this delta phi to the -1. This is the mass of the measure. Okay, not the mass. But now, okay, there is this guy. Look, maybe not too bad. Okay, if he's GFF, one has to be a bit careful what it is. But there is something a bit funny that if you look at this determinant, you should consider how it depends on phi to try to define your model, because phi again is GFF. And in fact, for us, it's not so convenient to look at this operator. There is one which is better, which looks more like really the true Witten Laplacian, which is by multiplying by exponential phi on both sides. Now we put a tilde here. So if I multiply on both sides, what is it? It's nothing more than dz bar exponential phi exponential minus phi times its adjoint. And this guy is somehow more natural. And there is a formula that you can find in the physics literature. Okay, we gave another proof in the paper. The determinant of this operator with the tilde behaves really nicely with respect to phi. So I'll give you the formula. It's really like Polyakov formula. Is it 50 minutes or 1 hour to talk?
1 hour.
1 hour. Okay, so now it's a fact, it's a computation. You look at this operator, at least if phi is smooth, not the GFF, but let's say you regularize your GFF, you compute the determinant of delta tilde now, not delta, but the one that you have multiplied on the left and right. So why, okay, when I do this delta tilde, I should keep in mind that I'm changing my field now. It means I need to introduce maybe a new field. I will call it nu, which is exponential phi times gamma. So I may well work with phi and gamma, or with phi and nu, for instance. These are two different coordinates. And for us, okay, maybe in the end we will work with gamma. But I just want to give you the heuristic why maybe it's kind of better to start with nu. And the reason is because this determinant has a nice formula. And we're doing a bit like physics, we're playing with things until we reach a formula which we can make sense probabilistically. That's the idea, essentially. So this guy is equal to determinant. Okay, maybe it could be made rigorously by smoothing the GFF and so on. So this is equal to the determinant of delta tilde 0, which is just, in our case, it would be just a Laplacian, the usual Laplacian. And the dependence in phi is really nice, actually. Okay, you have the mass of this guy, the L2 norm of this, square, you multiply by 1 over the volume, dg of the surface. And then there's a nice dependence which looks like the Liouville action, so it's 1 minus 2 pi d phi square minus 1/2 of okay, kg is twice the Gaussian curvature in my notation. So this is Gaussian, this is the scalar curvature of J, of G, time fixed. Okay, this is really like the Liouville action here. So you see that the determinant of phi is the usual thing. Okay, you have this term, and then this is the Liouville action. So now if I come back to my expression here, if now I do it with nu instead of gamma, this new parameter here, and this is d nu 0. Yeah, because okay, I didn't tell you, but in the path integral, it should be the Haar measure on H that should appear. So in fact, the measure here in the beginning should really be this d nu, so it should be like d of exponential phi gamma. Like the real, okay, of course we cannot make sense of this, but in the Wess-Zumino-Witten model, the measure, the Lebesgue measure, somehow on the group should be the Haar measure. And the Haar measure is the one, the Haar measure is, this is the Haar measure. It's really d phi, d of exponential phi gamma, which is this nu. Anyway, so maybe I don't really enter too much on this. Yeah, so this is the definition now if I use nu, and here this determinant now becomes this, and if I use my formula now, essentially it becomes time exponential minus exponential 1 over 2 pi d phi square plus twice curvature and phi. So this is now the marginal law.
And it's linear in phi, that term?
It's linear, well, not quite, I mean, there is Gaussian, but...
No, but the second term is phi.
Yes, exactly.
In Rhodes, you write d phi square minus 1 over 2 h.
Yeah, there's a minus 1, so the determinant to the minus 1, so there should be becomes plus. Or minus, okay, I have to be careful with the sign. I think it's plus, that's right. Okay, and now, if you remember, there was this chaos so that I want to take into consideration. So, my original action not here anymore, but remember the original action. This. The original action was exponential k and the Wess-Zumino-Witten model. So originally I had exponential f of phi maybe gamma exponential minus k over 4 pi integral of d phi square dt, and then minus this plus this 4 exponential minus 2 phi dz bar gamma to the square d phi and d of exponential phi gamma actually. This is the natural integral measure. And here, because of this k, you could really see that phi is not a GFF, but it's a GFF would be when k equals 1. So it's a GFF multiplied by square root of k. So here phi, if you want, square root of k and phi is equal to GFF in terms of flow. So there is a scaling due to this k that one should consider. Okay, so this is important. So now if I gather everything, I have a proposal for my Weiss integral. So proposal now for the probabilistic definition. Which is the f Wess-Zumino-Witten is equal. Okay, I have a GFF, so I have a determinant of Laplacian to the -1/2 over the volume. So times the volume of my surface. Then I have the integral on the zero mod of my GFF. Then I have integral on the zero mod of my mu zero field here. So this is going to be equation now of f. So phi again I said is GFF plus its zero mod. And of course I have to take care of the zero mod of my field. So this is the usual GFF. And maybe there is square root of k now. Sorry. There is a shift here due to this thing. So this thing, remember, this was the marginal. And in my original measure, I have this k here. And this is k over 4 pi, so if you look at 2 pi, this is like shifting k by -2 actually. So in fact, this tells me that I should not take square root of GFF, but it's square root of k minus 2. Is that clear? This comes from this shift here, because this shifting is k here by -2 actually. So I have to put this guy, and then my new field, mu g. Sorry. And then I'm left also there is this curvature term. So exponential 1 over 2 pi time integral of the curvature time my GFF, so it's square root of square root of k minus 2 c plus the usual GFF. And I think I'm more or less done up to deterministic terms, so I have some determinant probably also. Determinant of Laplacian to the minus, okay, here is 1/2 actually. 1/2, and then determinant of Laplacian to the minus 1/2. So this is the proposal. And here I have the new zero also, which is the 0, 1. And then I integrate over c, and I integrate over the new 0 and t. So this is okay, the proposal for the Weiss integral. Of course, I didn't explain how we can define this nu. Remember, nu was exponential phi gamma. So now, okay, defining the nu probabilistically, it's a little bit more tricky. So what we do, we come back to gamma.
So can you remind what is nu 0 and nu g? Because you have two nu.
Nu 0 is the zero mod.
Oh, this nu. Okay.
It's the element in the kernel of this bar. Of this operator. So actually it should be exponential minus phi times a constant. So nu 0 is something, it's a constant times exponential minus phi if you want. This is zero mod of the field. The element in the kernel. So now what we do, we switch back to the gamma field. I will explain why. Because if you look at the covariance of nu, this is the inverse of this operator delta phi, not the delta tilde, the delta phi. And the delta phi is not as nice if you think of phi as the Gaussian free field. So in some sense, the gamma field is easier to define probabilistically. So once you have your definition here, you just change this nu into gamma. So of course, it change your f here into f tilde maybe. But the gamma field will be much better. So we start from this. We replace now nu by exponential phi gamma, and we define the gamma, which means basically changing the way you consider functional of your field. So now I want to explain you how to define the gamma field. So until here it looks almost rigorous, except that I don't know how to define this nu. If phi is the GFF. So now there is a bit of magic here. So there is a bit of magic because there is a lemma. I want to construct the gamma field, so I need to consider the green function of this operator, this delta tilde. And because it's factorized as a sort of d-bar operator, which is like conjugated, and it's adjoint, it means the green function actually can be factorized as the inverse of this one times the inverse of this one. So the kernel of the inverse, the Schwarz kernel of the inverse, is given as follows. So it looks like this. So delta phi tilde inverse. If I integrate it against two functions, like two products, this is actually given by the integral. So let me do it on the sphere. Sigma equal the Riemann sphere. This is simpler. So on the sphere, this will be given as follows. So this is T0 F and T0 bar F exponential 2 phi of x dx. What is T0? 0, maybe I use Z for the complex coordinate. So T0 of F is given by 1 over phi. So it's just the Cauchy, it's just the Cauchy integral. So it's the inverse of the d-bar operator. So this is z bar prime z bar minus some explicit function of z integrated against f of z prime. Z prime. And this rho of z is completely explicit. It's integral of z time the metric. So there is a, let's put the metric here. So the metric G on the sphere, I write it like this, G of Z and dz squared. This is the metric. Because of course I need the finite volume metric to define it. So this is basically the inverse of the dz operator, this is the Cauchy kernel. So what is nice is that the covariance kernel, it looks like a composition of two of these Cauchy kernels with a measure actually. And this guy we know how to define actually. Because remember phi is going to be square root of k minus 2. I think I messed up like my MGFF. Yeah, probably it's 1 over. I messed up the number, for example. It should be B. So B was.
You have a 2 in front of phi already.
Yeah. Messed up the number, I think. Where's the key?
You have 2B GFF.
Yeah, so here it's really 2B GFF, so phi B times GFF, where B is a function of K. Which now okay, it's K minus 2 here. So I think I probably messed up, it was, I think it was, this was 1 over square root, so minus 2. I just did the scaling one. So this is B. So now you observe that this guy is less than 1 if k is bigger or equal to 3, or strictly bigger than 3 actually. And this now becomes Gaussian multiplicative chaos. So this measure we know how to define using probability. You regularize the field, you weak order, and this converge to a measure that Liouville and Anti and so on was included by Clark converge. So that's the way we define the covariance. The covariance is well defined, measurable with respect to the GFF, and then we define the gamma field using this covariance kernel by using this Gaussian multiplicative chaos. And then we have our path integral now. So in the end, the path integral is as follows. The conclusion of this is that f Wess-Zumino-Witten, we define it as, okay, there is a determinant, let's say on the sphere to start, there is a determinant with respect to g to the power minus 3 half times the square root of the volume of the sphere, for instance, sigma is the sphere, multiplied by, okay, you have a double integral in the 0 mod, so there is R, there is C, then there is expectation of f of phi, so it's like c plus xg. So now we can always change b times c plus xg, gamma, and then there is this curvature term, which was above. It's 1 over 2 pi integral of the curvature time b times c plus xg, and gamma is gamma 0 plus gamma g, dg, and then dc d gamma 0. So this is the definition for the path integral, where gamma is defined by its covariance, so conditional on phi, on GFF, gamma of z, gamma bar of Z prime is given by this inverse here, by the delta tilde minus 1 by ZZ prime. And then the expectation of gamma and gamma Z, gamma Z prime is 0. So it's a Gaussian field, and okay, we show this makes sense and so on. And maybe just 1 minute to say the correlators. So the correlators, they are, in physics, the one they are intrinsic, the primary field, the vertex operator. They are particular functional of this field. And the correlator are these guys. So the vertex, operator, to define the correlation, they are given by exponential alpha j phi at xj plus mu or alpha gamma z plus minus bar, I don't know. So these are the correlators. So they depend on two parameters, alpha and mu.
So alpha and mu live in what space?
So mu is a complex number, and alpha is it lives in the real number. But okay, to define the correlation, there is this, a bit like in Liouville, there is a Seiberg type condition for integrability due to, well, for instance, there is a zero mode integral. So there is some condition on the correlation to be well defined probabilistically. But, and actually, the conformal weight.
You continue to all alpha and then you analytically continue to all alpha.
No, this we didn't do. We do only on the real line for the moment. And I should say that the conformal weight delta, they only depend on alpha, not on mu. Okay, if you want, I can give the formula, but and they are the usual one of the Wess-Zumino-Witten. So mu, you should think of them more as a sort of moduli parameter, actually. They're related to this parabolic structure on homomorphic vector model. So this is the starting story. And then if you want to define the Guillarmou, the idea is to change the action by gauging. So you add a connection form in SL2C, and you deform the connection form. So here I wrote you the simplest case, but in fact to define really the model and deform it and to construct the Guillarmou structure, one should add something to the action to generate the Guillarmou. And then it becomes a bit tricky because the choice of this field phi and gamma, they will change and they will not be canonical. Sometimes they will depend on the choice of background gauge. For this we use certain tricks. I just wanted to explain a bit the idea, at least in the simplest case, how we can construct. It seems to be a good model because we recover like a certain formula that they find in physics. In Teschner, for instance, and Riemann. Okay, so I hope this was convincing.